Hello everyone. So again, welcome back to the latest lecture session. So in the last couple of sessions, we have been looking at, or we looked at a particular case study, let's say, with respect to in situ chemical oxidation, right? And now we are going to move on to the relevant topic that we discussed briefly, maybe a few sessions ago, right? That was surfactant extraction, right? So surfactant or surfactant based extraction, let's say, right. So until now we have looked at in situ chemical oxidation, let's say, or the relevant and the relevant case study, let's say, and we did briefly discuss surfactant extraction, but let's just have a quick recap of what we have been up to now, right. So let's just look at the condition that you would typically face out there. Let's say if a chlorinated solvent has what do we say, permeated through or contaminated the relevant subsurface, let's say, right. So what can you have if this is the subsurface and this is my groundwater level? Well, it won't be like this, there will be some slope or gradient, but let's go with that now. So let's say there was some spill here and the DNAPL came out here, let's say, and if it's DNAPL, it will go through to this semi impermeable layer at the bottom, right. So let's say this DNAPL reached here, let's say. So if I take this particular sample, let's say, right, if I take this particular sample, or if I am, for purpose of understanding, if I represent that here, what am I going to have? I am going to have the soil particles, right, and obviously the water, right. So if we look at this particular sample and I take that out, let's say, and try to visualize that, what will I have? I will have soil, obviously the groundwater, and what else? I will also have, let's say, groundwater, I will represent by just a few dots, let's say. Also I will have NaPl, let's say, please excuse my poor drawing skills. Let's just have this blob as this or assume that this is the NaPl, okay, right. And you will also have some of the NaPl dissolved in the water, right, and you will also have the NaPl adsorbed onto the soil now, right. You will also have some of the NaPl adsorbed onto soil. So these are the three what do we say, phases that we have. What are they? So as in the NaPl dissolved in the water, NaPl adsorbed onto soil, and NaPl staying as NaPl itself, right. So in the context of pump and treat, I believe we looked at pumping this out, right. So pumping out water, relatively easy depending upon the site conditions again, obviously, right. But let's say pumping out particular contaminants that adsorbed onto soil, as we saw, I think the factor of what do we say, the time required, let's say, to pump out the relevant contaminant, let's say, increases by, I think, a factor of 10, obviously depending upon the amount of contaminant that's adsorbed onto your soil, right. And then we looked at another case, let's say, when we have NaPl, even a very minor fraction, I think, right, I think 0.1% volume, let's say, or so on, or 1% volume. We saw that it takes hundreds to maybe, I think, a few thousand years to pump that out, right. So pumping out the relevant water and trying to remove the NaPl or such when we have desorption and such, or assuming desorption, right, that, as we saw, wasn't a feasible option. So what can we do now, right. So we can introduce a phase, let's say, that dissolves this NaPl and also, let's say, tries to desorb the relevant contaminant into this particular phase, let's say, right. So the phase that we are going to look at and the one that we are going to introduce is the surfactant, let's say, right. Surfactant, right. So what's its role now? So let's say in this particular role, what am I going to do? I am going to introduce a lot of surfactant, right, and then this particular surfactant, after relevant equilibrium, let's say, I am going to pump that surfactant out. Surfactant relatively easy to pump out again because of what do we say, its ability to form a surface, let's say, or its ability to let's say form at the interfaces. Again, we will look at those facts aspects, please. So surfactant, I guess, right, what's that, what's its primary role? Typically it ends up or acts in such a way that it ends up decreasing the surface tension, let's say, right, increasing the surface tension, right. So this is obviously a property of the surface energy, let's say, right, which is more or less, let's say, energy per area, right. And that, I think, as we looked at, right, this is the energy, force times the distance here, let's say, and here's the area, let's say, right. So, we end up with force per unit length, right. So, surface tension more or less, right. Again, what does this surfactant do? Typically anyway, typical action of surfactants is that they decrease this surface tension now, right. Again, people might have seen or certainly heard of surface tension, I am sure, or seen or visualized examples at surface tension. Typically, let us say when you have, let us say, what do we say, in a jar of water, let us say maybe an undisturbed water, let us say, and you have what do we say, a slight bubble, and even if you can float what we say relatively minute pieces of particles on that. Again, why is that? Because there is surface tension on the surface obviously of these these surfaces, let us say, or the water molecules. As in, maybe if I can represent it in a layman's terms, if this is a water molecules, let us say, right, and this is how the forces of attraction, let us say, if I can call that, right, are going to be, let us say, right. But at the surface, let us say, right, they do not have any force of attraction in this direction, right. So, what do they have? There is increased force of attraction at the surface anyway, right. So, out here, let us say, they have force of attraction in such ways between different water molecules, let us say, right. Again, this is the case with respect to water anyway, a generic case. Again, we are deviating from it, so I won't go further. But again, the key is that at surface you have what do you say, fluids typically have surface tension now, right, and these particular surfactants that we add are going to decrease this surface tension now, right. And how is it possible, let us say, right. So, when we say surfactant, what does it have? It has a head and a tail, let us say, right. And again, surfactants, right, again you can think of what you use every day, let us say, either soap to wash your hands, let us say, or the detergent that you use to wash your clothes, some examples of surfactants. But obviously, the function is that typically you have a hydrophilic head and a hydrophobic tail, right. So, the key aspect is that this particular surfactant has a head and tail, right. The head, which is hydrophilic, or wants to or has an affinity to what we say, water, and hydrophobic, which obviously wants to stay away from water, let us say. So, let us say, how does this act now? Let us say if there is water out there, and how does it orient itself? If this is water, let us say, in a container, so it is going to they are going to be oriented like this now, right. And in such a manner, let us say, they end up decreasing the forces of attraction between the water molecules, let us say, or in this case, let us say, the fluid at the surface, right. So, thereby they decrease the surface tension now, right. So, again in such a manner they end up decreasing the surface tension now, and this is how they orient. Why is that? Obviously, as we just mentioned, the head is hydrophilic, right, it has an affinity towards water. The tail is hydrophobic now, right. So, it does not have an affinity for water, or rather wants to stay away from water now, right. So, this is the key aspect for almost all surfactants, right. And again, let us look at the aspects that are involved here, let us see. So, as I keep adding surfactant to the solution, let us say, right, what is going to happen now? So, I keep adding to surfactant to the solution, some of it will be dissolved, let us say, right. So, let us say if this is the concentration of surfactant that dissolved, as I keep adding it, the concentration of surfactant that is dissolved keeps on increasing. But after a certain threshold, though, it is constant now, right. The one that is dissolved one accumulates at the interfaces now, right. So, that is something to keep in mind, we will come back to that. So, as I keep increasing or keep adding more concentration of surfactant, let us say, right. If I keep adding the greater the concentration of surfactant, after a certain time the concentration of the surfactants that is dissolved, let us say, is constant, it does not increase. So, what happens to all the surfactant that I am adding now? So, that turns into a phase called the micelle phase. So, this is the dissolved phase, right, and this particular phase is the micelle, let us say, right. And again, when is this formed? Only after a critical micelle concentration is formed, that is why this is called CMC. Again, let us just try to understand this figure. So, initially when I keep adding the surfactant, right, As I go in this particular direction, adding the surfactant, the dissolved concentration of the surfactant keeps increasing now. But once we reach this critical micelle concentration, right, what happens now? Obviously, the dissolved concentration stays the same, right. There is a maximum, think of it as the solubility, let us say, right. So, it stays the same, right, but now you start forming these particular particles, if I may say, called micelles, let us say, right. So, obviously, if you want to form micelles, you will need to add enough surfactant such that the critical micelle concentration has been achieved, let us say, or reached, right. So, again, before we go into further discussion of micelles and why they are important, let us try to understand what happens now. So, I keep adding what we say surfactant, let us say, and where does it first go to, let us say, the dissolved one, let us say, it goes at the interfaces. As we discussed, let us say, it tries to, or it will first occupy the interfaces, right. So, once I for a particular that site, let us say, all the interfaces are occupied by the relevant what do we say surfactant, right, or there is no more interface to be occupied by surfactant, let us say, right, and then you are going to have formation of these micelles, let us say. And what is the typical shape of these micelles? So, it is something like you have the hydrophobic tails inward and hydrophilic heads outward. So, this is the typical concentration of a micelle, let us see, right. So, typically first you will have the interfaces that are occupied, right, interface, that is self explanatory, and once all the interfaces are what do we say occupied, let us say, and then you have you also reach the critical micelle concentration, then you start observing formation of these micelles, let us say, right. So, what is the key aspect in this particular micelle and why is that relatively important now, right. So, one aspect obviously is when you what do we say have these surfactants, let us say, occupying the interfaces, again decrease in surface tension, let us say, right, and depending upon the kind of contaminant or such, pumping out is relatively easier, that is one aspect, or even let us say to stabilize colloids, that is going to be easier. So, we are going to come back to that later on again, but what is the relevance of these micelles now, right. So, if you think of this, let us say, or if you look at this, pardon me, you are going to see that all this particular what do we say part of the relevant micelle is hydrophobic, let us say, right. So, this itself acts as a non-aqueous phase, right. So, keep that in mind, as in earlier we came across the term NaPl, non-aqueous phase liquid, either LNaPl or DNaPl, right, but typically we have applied them to the relevant contaminants here, right. And what was the property of these contaminants that made us call them as non-aqueous phase liquid? Typically they are hydrophobic, right. So, these contaminants were those contaminants that were hydrophobic, right, and such we typically call them as non-aqueous phase liquids, right. So, in the same case here again you have a non-aqueous phase within the micelle, and what is that now? That is because of the orientation of these particular surfactants, let us say, and again here you see that all the hydrophobic tails, let us say, are bunched together, if I may call that, or explain that in that manner, and you have the hydrophilic what do we say heads oriented outwards. So, now you have a non-aqueous phase. So, what is the relative importance here though? The key is that now that you have a non-aqueous phase, right, or let us think of it this way now, what is the driving force for this particular contaminant, let us say, to be adsorbed onto soil? It is that you have organic fraction in the soil, that is again acts as, let us say, a reservoir for these hydrophobic compounds. Similarly, here you have a non-aqueous phase. So, this can now, let us say, act as a reservoir for the hydrophobic contaminants, right. So, now you can have desorption of the relevant contaminant from the soil or dissolution of the NaPl into this particular micelle. So, let us just try to visualize that. So, let us say earlier you had the soil and the compound adsorbed onto that, and also NaPl blob, let us say, right. And now what happens is that as I introduce my micelle, let us say, or the surfactant after CMC, let us say, has been achieved. So, what happens to these particular contaminants here, let us say, they would now, let us say, what do we say change phase from, let us say, being adsorbed onto soil into the micelle phase, let us say, and similarly some of this particular blob, let us say, will dissolve, or when I say dissolve into this particular what do you say, non-aqueous phase inside the micelle, right. So that is the key aspect. And once you, let us say, you add enough surfactant to dissolve either the entire NaPl or desorb most of the contaminant on the soil, you can then pump the surfactant out. It is relatively easy to obviously pump the surfactant out, right. So that is something to keep in mind, right. So let us look at some of the aspects, let us say practical aspects, how this particular mechanisms, if I may say so, how these how addition of surfactant, let us say, helps us, let us say, in our remediation goals. So one aspect is that it helps stabilize colloids, let us say, right. So let us say you had different colloids, let us say, suspended, let us say either blobs, let us say, or colloids, let us say, you will addition of these particular surfactants, let us say, now helps bring together these colloids, let us say, and help them stabilize, let us say. So that is one particular way, right. And the second aspect is that, let us say, when you want to, or when you have soil, let us say, and you have a blob of NaPl, let us say, right, and you want to squeeze this blob of NaPl through this particular pore space, let us say, as in you are trying to pump it out, let us say, right. So here, let us say, because of what do we say, you want to pump it out, let us say, because of the energy required, let us say, soil in this case is relatively more polar, if I may call that, relative to the NaPl, right. So you are going to have issues with pumping this or squeezing, if I may call that, squeezing this particular blob of NaPl through this particular pore, let us say, right, or pore space, pardon me. So what and how will this particular NaPl, not NaPl, the surfactant aid now? It will aid in such a manner that by helping in forming a surface, right, for which the energy is obviously required, right. So by helping in forming a surface, let us say, right, it will make it easier for the relative, this particular blob to be squeezed through, right. So when pumping it out, that it helps in that manner. And as we just discussed in the form of, or when we talk about sorption, right, as in earlier, let us say, compounds that were adsorbed either onto the soil or were in the phase of NaPl, now let us say, will now be sorbed into the micelle, let us say. They will now be sorbed or adsorbed, if adsorbed might not be the great term, but sorbed into the NaPl now, right. So three cases, as in stabilize the colloids, helping, what do we say, to squeeze through the relevant NaPl, let us say, and also in sorption, let us say, right. So three cases. Obviously these are more physical characteristics, but here obviously we need to look at the aspects relevant to equilibrium now, right, with respect to equilibrium. Why is that? Again, similar to the case when we had just water and the soil, there is going to be a case as in when we had, let us just have a quick relook now, as in if I have just soil and water, let us say, all around, and then I introduce some contaminant, what is going to happen after I let the system reach equilibrium, depending upon the type of compound. Let us say some of the contaminant will be dissolved in the water, some will be adsorbed onto the soil, let us say, right. The fraction will depend upon its hydrophobicity, let us say, or the octanol water partitioning coefficient, right. So again, now there is going to be an equilibrium between two phases. What are they? Soil and the relevant water here. If there was NaPl, let us say, that is a third phase. So there would be equilibrium between all the three phases, between the water phase, the one dissolved in the water phase or the aqueous phase, soil phase, and the NaPl phase. But now we are adding the fourth particular phase, which is the surfactant, right. So there is going to be an equilibrium between all these four phases, and that is something that we are going to look at, let us say, right. So obviously we are going to look at the case of equilibrium. So let us look at the case when we have only, let us say, what is it now, the aqueous or the dissolved phase adsorbed onto the soil and NaPl present, let us say, right. So this is something we have looked at, but let us just try to understand the total mass at time equal to 0, right, initial total mass, let us say, what is that equal to. So obviously it is, let us say, if porosity of the relevant system, total volume, and concentration of the compound in the water, let us say. These are the three terms we have typically used. So I have epsilon V into C, right. So this obviously gives me the mass of the relevant contaminant dissolved in the water. Again, we did look at this, but let us look at it again. This is pore volume, right, volume of pores by total volume of pores, which is, when I say volume of pores, obviously this is occupied by water, right. Volume of pores by total volume into total volume into concentration is mass of contaminant per volume of water. Volume of water means nothing but volume of pores in this context, right. So, all these relevant terms cancel out and I am left with mass of the contaminant that dissolved in water. So, that is what we have here epsilon Vc plus what else? We are looking at soil. Similarly, I believe we looked at this volume, the bulk density of the soil times the mass of the concentration of the contaminant in the soil adsorbed onto the soil, right. So, that is Q. Q is the concentration of the contaminant adsorbed onto soil as in mass of contaminant adsorbed onto soil per mass of soil, let us say, right. So, that is what we have. As we know, it is going to be in equilibrium with the concentration of the relevant what we say compound dissolved in water, right. I think we were looking at a linear relationship or considering a linear relationship, we have Q equal to Kp into C, that is something we looked at. And if we have NaPl2, right, obviously it is going to be within the relevant or be present within the pore space, right. So, let us say the fraction of the pore space occupied by the relevant NaPl is S equal to the fraction of pore space occupied by NaPl, right, and then the volume will be epsilon V, right, and then we have the density of NaPl, right, times the mole fraction, let us say, of the relevant contaminant that you are looking at, let us say in the NaPl, right. So, typically if it is a pure NaPl that we are talking about, which is the contaminant, this is going to be this as an x is going to be equal to 1, right. So, since here we are considering a fraction that a fraction of the pore space is occupied by the relevant NaPl, we also need to deduct that particular case here or take that into account, right. So, again what do we have here? This is the mass of the contaminant dissolved in the water, this is the mass of the contaminant adsorbed on soil, this is the mass of the contaminant what do we say in the NaPl phase, right. So, in this context we look at retardation factor which affects let us say your ability to pump stuff out or such, right, and what is that? That is nothing but M total by mass of contaminant that is dissolved, let us say, right. So, that is nothing but equal to M total by epsilon or 1 minus Eps as epsilon Vc naught, right, depending on how we are terming that. So, this is what we have. So, let us look at the scenario or the change scenario when we add the micelle, let us say, right. So, when we are adding the micelle, obviously there are a few factors that we need to keep in mind, as in what are they? So, as we know, firstly it is going to be in the dissolved phase, right, and only then will you have formation of the micelle, right. So, the total surfactant let us say will be equal to surfactant in the dissolved phase plus surfactant in the micelle phase, right. So, that is something to keep in mind, and only the micelle phase can adsorb the relevant contaminant, right. So, we are typically now going to look at this particular case, and what is this? This is nothing but S micelle is nothing but amount of surfactant amount of surfactant in micelle per volume of water, let us see. Okay. So, that is what we have here, that is the S micelle here, right. Again this is the amount of surfactant in the micelle phase for the per volume of water, let us see. So, now let us try to understand this particular or how this particular scenario is going to change when we add the surfactant, right. So, when I add the surfactant, let us say some of the mass of the contaminant will be in the micelle, right, and that I am going to represent as Y, which is the mass fraction is equal to the K micelle water partitioning coefficient. So, this is similar to let us say your K octanol water partitioning coefficient, as in what does octanol water partitioning coefficient give you an idea about, as in if I have octanol and water and I introduce a contaminant, and then I will get a fraction of the concentration or the ratio of the concentration of the compound in the octanol to concentration of the compound in water, let us see. So, this will give me an idea about how hydrophobic it is or such. So, similarly I have the K micelle water partitioning coefficient, and that times let us say x, let us say this is again mass fraction of the compound in the relevant water, let us see. Keep in mind that this x is different from the other x variables that we have used earlier. So, maybe let us use this. So, y is the mass fraction right. So, that is nothing but y equal to mass of contaminant in the micelle by mass of micelle or amount of micelle here, right. So, that is something to keep in mind. Again, what do we see here? It is an equilibrium between the contaminant in the water, which I am representing by x here, right, and also the contaminant in the micelle. Again, it is an equilibrium between 4 phases now: surfactant and NaPl, soil and water, right. So, again all of these are tied up by their, what do we say, the different relationships obviously with the concentration in the aqueous phase, and this is one such relationship. So, now let us try to write this down, right. Now, I am going to, let us say, initially I had C naught, let us say Q is again equal to Kp C naught, right, in the initial case anyway, right. C naught is the initial concentration, let us say, of the relevant contaminant in the what do we say, in the water. But let us say one thing to understand or keep in mind is that if there is NaPl, right, which is the pure solution, let us say, or if I am assuming that it is pure solution, let us say, of the relevant contaminant or the pure contaminant, what is C going to be? And if the equilibrium has been reached, again let me reframe the question. Let us say if you have the pure contaminant as the NaPl and you have that having reached equilibrium with the water and the soil, what will this C be? C is again the contaminant concentration in the water, let us say. It is going to be the solubility, right. Solubility will give you an idea about the maximum concentration of the relevant compound that this particular solution of water can hold, right. That would have been the C solubility. Again, that is something to keep in mind, right. So, again let us come back to this case and write down the new M total. So, M total will be is equal to, it is going to be the same, this M total is still the same, the total mass has not changed, right, but it will now change within this particular what do we say case, as in let us say 1 minus S epsilon Vc, it is now going to be something else, right. Why is it something else? Because I added surfactant and some of the concentration of the contaminant will be taken in by this surfactant, let us say, right. So, the C is not going to be C naught anymore and V rho B into Q dash, right, see, and what is Q dash? That is nothing but equal to Kp into C, right, this C here. What is Q? Again mass of the contaminant adsorbed onto the soil per mass of contaminant in the relevant not in the what do we say water, it is mass of contaminant adsorbed onto soil per mass of the relevant soil, right. So, again that is going to be depend upon or in equilibrium with the concentration of the contaminant in the water, that is what we have here. And if we still have the relevant NaPl, let us say, and X here, right. So, this S might decrease. Now, this S might decrease. Why is that? This S might decrease because as I add surfactant, some of the relevant NaPl will dissolve and move into the micelle now, right. So, obviously I will have S dash here, S dash X NaPl, and now let us represent this particular micelle, let us say. So, I am going to assume that it is going to be in the same pore volume, let us say. So, it is epsilon V, right, and what else do I need to have? This will be the volume of water, right, volume of water. So, it will have to be multiplied by S micelle obviously, right, and then by Y, right. So, this is what we have, right, and again what is Y? Y is nothing but kmw into X, right. X is again the mass fraction of the contaminant in the water. So, how can I represent it in terms of variables that I have here? X will be nothing but C dash by density of water, let us say, right. So, here I have this relationship, but let us just try to understand that. Let me rewrite that here. So, the total mass of the contaminant is now equal to 1 minus S dash, I believe, epsilon Vc, right, plus rho B and V, I guess, right, rho B or V rho B Q dash. This is the contaminant present in the soil, plus S dash epsilon V, right, and what am I writing here? The NaPl case, right, X NaPl. So, this is all these set of variables give an idea about the mass in the NaPl, and now the mass in the relevant micelle, right, epsilon V, and what else do we have here? So, S micelle, and Y is nothing but kmw into X, and that is nothing but kmw into X is concentration of the water divided by density of water. So, that is what I end up having here, kmw, right, into C dash by density of water. Again, there are different terms or such, but it will make better sense maybe once you solve one of those homework problems. But let us try to understand why this is important now. Earlier the C or this particular concentration or C dash, if I may can call that, let us say, because I am calling that C dash here, was higher, let us say, right. Why is that? Because you did not have the micelle, but now C dash will typically be less than, C dash will typically be less than what do we say, C here, the earlier C naught here, right. And also S dash will be less than, yes, what is this S or S dash? It is the fraction of the pore space occupied by the NaPl. And why is that decreasing? Because now you have the micelle, right, and that particular micelle can absorb your particular contaminant. So the contaminant which is in the form of NaPl will dissolve and now change phase into the micelle case, right. So some of the contaminant that was in these 3 phases earlier would now have moved into this particular phase, mostly from these 2 cases though, let us say 2 and 3 rather than from 1, right. So that is the aspect to keep in mind. So here what is the retardation factor? It is still M total, which is the same by the amount in solution, let us say, but when we say solution, it obviously also includes the right, it also includes the contaminant present in the NaPl, not NaPl, pardon me, the micelle. So epsilon V S micelle KMW C dash by density of water. This is the new R dash. What was it earlier? It was R was just M total by the mass in solution. I think in that case it was epsilon V C naught or 1 minus S epsilon V C naught, right. So what is happening to R? As you see, R is decreasing here, right, R is decreasing. So the retardation factor has decreased. Why is that? Obviously because now I have more of my particular contaminant in solution. Again, keep in mind that I am considering that, or obviously that is the case, that logically that the micelle is also part of the solution, right. So that now more of the contaminant has moved from being absorbed or present as NaPl into the relevant solution. So looks like I am pretty much out of time, right. So I will continue this in the next session, but what is the take home message here? By adding the surfactant, we are either dissolving the NaPl or let us say desorbing the relevant contaminant from the relevant soil now, right. So the other case is that when we add enough micelle or enough surfactant, what is going to happen? All the NaPl is going to dissolve and most of the compound adsorbed onto the relevant soil will, what we say, be desorbed into the relevant micelle, right. So that is the relevant aspect, but I guess I will continue this in the next session, and thank you.